introduce this fellow. This is a wrecked airship from Guns Vickers Online. I'm going to be using this guy as an example, so I think he's going to come back a lot. All right, so when we're rendering, what do we care about? Colors, positions, probably some directions. All of these things are vectors, floating point vectors specifically. This is exactly what shaders support. This is about the only data type shaders support. So they're very recently, integer types have started being introduced to shaders. That's a new thing. Shaders deal with vectors specifically, not just single floating point types. Float, float 2, float 3, float 4 are 1, 2, 3, 4 element vectors in CG. Shaders deal with these vector types natively. It is just as fast to multiply 2 single floats as it is to multiply 2 4-element floating point vectors together. Again, it's because of the nature of the underlying hardware. So, on all these types, you have basic arithmetic operations. These are pretty familiar. Times and divide, in this case, are component-wise multiplication and division of the vectors. That is not proper vector multiplication. I'll come to that in a moment. You also have this weird thing called swizzling, which is that you can address the vectors by XYZW, RGBA. They're just alternate names for the same things. CG doesn't care if it's a color or a direction or a position. So you do some cool stuff. But you can also flip those around and recombine them in different ways. So I have a float, I can do float 3, I can do float 3.xyz, I can do .rgb, I can do .xxy if I want the x component twice for some reason, for some operation. And all of that is very fast and doesn't really cost you anything. So here's our first example snippet of some really simple CG code. This takes a normal vector, it turns it into a color that can actually be displayed. Assuming here the vector is normalized, so all its components are going to be between -1 and 1. Well, a negative color doesn't mean anything, so we add 1 between 0 and 2, multiply by 0.5, it's between 0 and 1. Now it's a perfectly reasonable color. What would this look like, you say? Something like this. So here's that same ship rendered in normals. So, as you can see, the blue sort of turned into the Z, the direction facing the camera in this particular example. The green roughly corresponds to Y. You can see the upper surfaces are more green while the lower surfaces are not. And you can see some red peeking around on the left side because that's where the world x-axis is. So, after the basic stuff, we have vector and matrix math, also matrix types. So you can do various your usual 3D transformations in Shaderland. Vector math is done as functions, dot product, cross products, reflection vector around a normal. Likewise, matrix operations like matrix multiplication and transposition, or as in the example here, converting a position from one space to another, a matrix transform of a vector, null the matrix by the vector.
Why is the position float 4?
Good catch. That is because to multiply something by a 4-element matrix, you need a 4-element vector. Typically, in typical usage, the W component of a position vector is just 1 in that case. You can also do this with a 3x3 vector in a normal position. But then all you can do is rotation. This is affine transforms in matrices. You need a 4x4 matrix to do both rotation and translation and scale. And finally, you have methods to access textures. I'll limit my discussion today to 2D textures and cube maps. A cube map is a 6-sided cube that you can look into via the normal. CG also supports 1D textures and 3D textures. Their 3D textures in particular are kind of weird and hard to work with, so I'm going to ignore them for the moment, but you can do some really cool stuff if you have an editor that lets you actually author one. Here's a very simple texture lookup. I have a 2-element vector that are my texture UV coordinates. I have this sampler 2D object that is referenced to a texture that has been filled in by the engine somehow. And then I just get a float 4 color out of that with the text 2D function. Fairly simple. And finally, you have kind of the usual suite of C math functions, trigonometric functions, exponential functions, what I will group as control functions, the various side math operations, max and min and floor and ceiling. Saturate is kind of a more unusual one. That's simply a clamp between 0 and 1. However, due to the nature of most graphics hardware, it is effectively free. It's literally a function that costs nothing to call, which is unusual. You also have loops and conditionals, while, for, and if. Most of the time, it's a bad idea to use them. Graphics hardware, the hardware level does not handle those very well. So typically, what your compiler will do, if you have a loop, actually it just unrolls that and does each iteration manually in the compiled shader. So having a loop that goes through a bunch of iterations just makes your shader huge for no apparent reason. Conditionals, until very recently, the way most graphics hardware handled conditionals was it would actually execute both conditions and then pick the one that it actually wanted to keep. This is all a side effect of the fact that graphics hardware is very, very specialized and very, very fast at the things it's good at. Things it's good at are vector operations. It's not good at loops and conditionals. I'm sorry, this is cut off. Well, there's nothing really on the other end other than some parentheses. So here's a basic lighting function. This is diffuse lighting right here. I have a normal vector, I have a light direction, take the dot product of them. That's I said a cosine was important earlier. This is the only part of the real BRDF that everybody uses. That dot product is essentially the cosine of the angle between those two vectors. And then we saturate it because, again, a negative color doesn't mean anything. And we now have a nice 0 to 1 lighting term. Multiply that by your color. Speaking of which, hey look, let's get a color. So again, we get a basic albedo, unlit color out of the texture based on our sampler objects and our UV coordinates. We take our diffuse term by saturating the dot products of the normal and the light direction. And we multiply a bunch of stuff together. The base color, the color of the light that we're shining on this object, some kind of intensity term for that light based on distance fall off or whatever, and that diffuse term. Pointedly, this says nothing about whether that light is a point light, a spotlight, a directional light, any of that. That is not CG's business. That is not the shader's business. That is kind of up to how the engine has configured it. No, actually I lied. I'm sorry. This basic lighting function is true for all of those types. Depending on your engine, Unity is actually kind of nice about this, which is why I fooled myself for a minute there. You may or may not have to deal with those special light types. Unity does some stuff to kind of mask that all away. But really, if you were doing things from scratch, you would probably have to have a slightly different shader for your spotlight, and a slightly different one for your directional light, and a slightly different one for your point light to handle all the different fall-offs and stuff. So that would be shader territory. Sorry. So, you saw some texture variables and some things like light directions and light intensities that I just kind of assumed were there. Because from the shader's point of view, that's exactly what you do. The shader has nothing to do with where those values come from. Those are passed by the engine down into the shader. If you are working on the very low OpenGL DirectX level, there are calls to set shader constants or uniforms, which are variables that will not change for the entire execution of the shader. And these could be global to your entire scene. These could be per material. It's going to vary heavily on your engine. But regardless of what your engine supports at base, typically you can extend this. You can add more. Unity, for example, has its fully extensible material system. You can add whatever the heck you want to your materials. You can also set shader globals, which are just variables that are available to all your shaders, regardless of what material is running, which you can use to configure new types of lights, strange alternate lighting conditions, etc. At, again, that low level, roughly what happens is the 3D API, Vertex or OpenGL, configures the rendering environment, which means setting all those shader variables up in from outside, uploads a bunch of meshes and textures to the GPU, and then selects the current shader and then executes that shader. This is a pass, or a draw call. When you talk about optimizing draw calls, it is because this entire process happens on the CPU down to the very bottom. Only the shader execution itself is on the GPU. This is frequently a limiting factor, which is why you try to minimize draw calls, because each draw call means doing all this configuration and uploading stuff fresh to the GPU. So, back to some Unity-specific stuff. This is how Unity handles its lighting environment. We have a whole bunch of different light types: ambient lights, point lights, spotlights, directional lights, light maps. It has two completely different rendering paths, forward and deferred, because deferred is not very customizable. I will mostly be talking about forward, but if you do things the way Unity wants you to, you can kind of use either. It also has this fancy light priority system where it will decide, based on intensity and distance, which of your lights get drawn per pixel in their own single draw call. Per vertex, it can batch a bunch of per vertex lights into a single draw call, or as spherical harmonics, which I will not go into the math of, but basically lets you wrap an arbitrary number of lights into a single set of, I think, 36 constants, and just do the math in the shader from there. Spherical harmonics is great for having lots of lights, but it's really, really bad at lights that are close to the surface that you're rendering. So it's only useful for kind of low priority stuff. Unity also provides you with a thing called Shader Lab. You write Shader Lab in files that end with the extension .shader, which is unfortunate because Shader Lab isn't actually a shader. Shader Lab is Unity's proprietary format for configuring that rendering environment that I was talking about. This is where you set up your per material properties. This is where you set various other rendering state variables, like your blending options, like your depth testing. You have some control over draw order through the render queue, which is important, particularly for transparent stuff. And then in that, in Unity, you would embed your CG code to do of the actual shader. Unity also has this fancy thing called surface shaders. Surface shaders are an attempt to wrap up all the fancy multiple light types and multiple rendering paths that Unity deals with, and let you only have to enter the bare minimum of code in order to do something. It has a lot of advantages. You can use all of Unity's built-in lighting options and shadow options, etc., without having to rewrite all those shaders yourself. You can use it mostly with both forward and deferred lighting, although there are some limits on using surface shaders in deferred. And it heavily reduces the amount of boilerplate setup code that you have to put in every single shader. But ultimately, it is limited and it hides what's actually going on. So I'm going to talk about it for a little bit and then move on to the guts. Surface shaders are all about setting a bunch of surface properties that Unity will then run through its lighting function. The albedo, the unlit color, the alpha, the emission, a gloss turn, a normal. I'm sorry, I previewed these slides on a wider monitor than this projector supports, apparently. There's a very simple surface shader function. A lot of this is familiar from my previous examples. It's look up some textures from Text2D and some UV coordinates that got passed in magically. We set the albedo to the surface shader. We call another function to do some fancy stuff on the albedo. And we call another function to do some fancy stuff to the emission term. In this particular case, this is adding another light to it, since the emission will only get run once for the object, not every single pass. like some of the other stuff will happen for every single light that illuminates this object. This is the easiest way to just kind of add another global ambient light that is special to a surface shader. So, some examples about what these are. This is a function for getting an ambient light out of a cube map. This is a very handy technique because a cube map gives you a whole bunch of nice soft lighting variation over that whole three-dimensional surface. It's very good for large outdoor scenes where you get reflected light out of the sky and slightly different reflected light coming off the ground, maybe different light on one part of the horizon where, say, the sun might be setting versus from another part of the horizon. And you can encode all that into a single texture and do it as a single texture lookup, which is quite nice. Now, this is weird. I'll show you what this does. This is about modulating the the albedo of your texture by another texture. It gives the effect of painting a decal over your object. So I have this fancy little Zeppelin thing here with some gears painted on it. The gears are red. I don't like red gears, I want blue gears. This one's going to be old. So the red disappears. And let's have some blue. I'm sorry. That was the wrong material. Shaders work apparently. There we go. This here, I set a color on the material that then gets painted on through that additional texture lookup on top of the normal one. And this is all done before lighting is applied, so shadows still take effect, bump map still takes effect underneath this. I can also bring in several decals at once. Texture I'm working off of here simply has two decals painted into it, one in each channel. So this is a cool technique for doing some customization stuff. You can now, say, have your players input the color they want their Zeppelin to be painted. We use a very similar technique for doing skin tone on our characters, so that can be an option that they just select. Is also, so this takes each, for each color in the output, I want to take the red, green, or blue channel of the paint map and modulate it by the alpha channel of the incoming color and multiply it by the RGB of the incoming color. So that I get so I can do up to 3 overlays in a single one. Overlay, this is the function that will make your artists love you. This is Photoshop's overlay blend mode. This is possibly one of the most useful things you can do when you're trying to do fancy multi-texturing nonsense. Get your artist to tell you what Photoshop blend mode they want you to use and implement it in your shader. That link is right there. Right there is to all of the Photoshop blend modes. We will put these slides online afterwards so you can go find it later. This is a fantastically useful tool. Sure.
So where like you find the position on this view? The shaders position.
I'll come to that. We're not there yet. All of this right now is executing for each pixel on the rendered object. I have some information given to me about UV coordinates at that pixel, and from that I look up into my various textures and do the mapping from there. Under the hood, this is kind of what I was talking about earlier with the things that surface shaders hide. There's a pass for a whole bunch of stuff baked together. Your ambient term, your light maps, your vertex lights, your spherical harmonics lights, and one directional pixel light. and then additional passes for every pixel light you want beyond that. And all of these are unique, very long shaders that surface shaders are generating under the hood for you. You can turn debug on in Unity and see them. It's quite useful, actually. Gives some brightening. But if we wanted to go down straight to the low level, we deal with two things, Vertex shaders and pixel shaders. We have our external values that are set for both of them, that are available to both of them. The vertex shader is then a little snippet of code that runs for each vertex in the mesh. Then the graphics card internally does some interpolation between the results of the vertex shader, or points on the triangles between the vertices, and for each of those runs the pixel shader. Technically the fragment shader, because it doesn't render just for all the pixels you see. Depending on depth testing, anti-aliasing, and some other things, it may render many more times than the number of pixels you actually see. But that ultimately outputs the color. To your question earlier, if you wanted to move things around, you have kind of two options. Either in the vertex shader, you alter the position that you got in and deform it. You can do this to do, say, water ripples and that kind of thing. Or in the fragment shader, you warp the UVs as they come in, according to some math function or modulated by another texture. I'll show an example of that later. Here's a very stripped down example with most of the boilerplate removed of a vertex and fragment shader pair. That struct I declare at the top is the structure that will be interpolated. It's returned by the vertex shader and passed into the pixel shader by the graphics card. The colon syntax is referred to as a semantic. That is done to tell the graphics card what this is and how it needs to treat it. Most graphics cards still, I think, this is changing in very recent Shader API versions, support up to 8 of these text coord semantics, text coord 0 through 8. Can't have more than that. This is a hard limit, unfortunately, and your shader compiler will yell at you. However, those don't need to be used strictly for textures. You can use those for just about anything. Position is a slightly more specialized one, and you can see that syntax return again at the fragment shader to tell the graphics card that I'm returning a color rather than, say, a depth value or something similar. So, what would you do in a basic vertex shader? I have some data passed in about the original vertex in local object space. Well, I want to convert that to projection space because the shader is running in view. So multiply it by a matrix that Unity, in this case, handily provides. Then I want to take my incoming texture coordinates and maybe I want to scale that and tile it according, again, if you're used to Unity, it provides some options for these on your material. So I do this transform texture function on that. Again, assign it to UV coordinates of that structure. That then gets passed on, interpolated between for each of the pixels on a triangle defined by the 3 vertices that ran for, say. And for each of those, simply look into the texture by the passed in UV coordinates, return the color. And notice the position has vanished. This is because that has been used internally by the GPU to tell you where on the screen this fragment is actually going. Unfortunately, it is not actually exposed to you when it does this. So if you actually need the world position or the object space position for some effect, you have to do it yourself in another semantic, in another interpolated value under a text coord semantic. So, talked a little bit about rendering an object using Vertex shader to modify or simply transform its vertices, run the pixel shader to modulate the color, do whatever fancy effects you might want. The other thing you can do with shaders is a PostProcess effect. PostProcess effect is simply a single quad, 4 verts, 2 triangles, drawn over the entire screen with an image of the scene as the as an input texture. This allows you to do real-time color correction. This allows you to do bloom and glow, fancy depth of field effects. The limitations are few here. You can do quite a lot of fancy things if you give yourself all the data you need. And also, PostProcess Effects have a distinct advantage in that they are not per object. They only run for the pixels that are actually visible, which for complicated scenes means it's often cheaper to push some of the fancy effects into a post-process effect in order to make them faster. The flip side of this is that a post-process effect always needs to render to another buffer because it needs that input image of the original scene. And depending on the hardware you're using, that process can be very slow. In particular, on mobile devices, this has historically not been very good, although it's getting better. And also, that needs to happen for each post-process effect. You can chain these together to do a bunch of them at once, but that means that you need a new buffer for the output of each previous post-process effect before you feed it into the next one, so that memory usage can stack up. Now, I'm going to show you, kind of silly, but I think it's cool, post-process effect for making it look like your scene has been painted by someone with perhaps slightly bad vision. This is kind of a simplified thing. So, as you can see, I've taken the normal image and converted it into this kind of squishy version composed of a bunch of blotches of single color, something like you might get with a paintbrush. And I'll show you what this did. All right. So, I'm going to render a scene in brushstrokes of solid color. Here's the interpolator structure I'm going to use. Position is familiar. I'm going to use a whole lot of UV coordinates for this. You'll see why in a minute. I've cheated by batching them all into an array. So here's my vertex shader. Normal, multiply the position, get it into view space, multiply the UV coordinates to get them into proper scaled space, whatever, not a big deal. That off parameter, this is simply a shader space calculation of the size of a pixel. The main text pixel size variable is one Unity provides. Size is something that is passed in by my code. Then I do calculate a whole bunch of UV coordinates. What I'm doing is generating a circle of sample positions, made of them around the central point, which is where I actually am. Then that gets all passed into the pixel shader, where for each of those 9 sample positions, I look up the color in the original input image, I calculate a luminance value, how bright the color is, and of those 9 samples, I pick whichever color is brightest. So now each pixel looks up into its immediate neighborhood, picks the color that is brightest in that immediate neighborhood, and uses that color instead of its original. And this results in these blotches of where pixels decide to share color. If I go to material, focus is going to be visible. I'm sorry, I was going to try to show you the samples spreading out until they became visible as individuals, but that appears to not be working in this version for some reason.
I think the first one that you started playing with actually worked. The second one didn't.
Fiddle with this more later. Let me see if I get through the rest of this first. A couple other weird shader functions I use in here. Lurk, linear interpolation. You do some version of this in pretty much any 3D engine, but exists in shader language too. Step is a goofy function that compares two values, and if I believe the second is greater than the first, it returns 1, otherwise it returns 0. This lets you do conditionals that aren't actually conditionals in shaderland, where conditionals are expensive. So, you can do a post-process effect that takes your single input image of your original scene. You can also get fancy and do fancier post-process effects that use multiple input images. Sometimes you want to generate these multiple input images by rendering your whole scene with a different shader. Unity provides a special facility to do this camera.render with shader function. And a facility for storing the output results of these, a render texture. This is a render target in low-level 3D API terms. So also, one of the most common things to do with this is to get your graphics card's depth buffer into a texture. Depth buffer is normally used for testing objects to call them out early, but you can also use it for fancy post-process stuff like depth of field and such. That's a rough approximation of what the depth buffer might look like, once converted into a texture, where the color, the intensity of the pixel, indicates how far into the scene it is. Technically, this is backwards because of the way depth buffers internally are stored. Black is next to you, or there's no color at all, and white is as far away as possible. This is reversed because this is a whole lot more sensible and easy to work with if you're doing it yourself anyway. I should also mention that I said converted to a texture. Most of the time, you do not actually get access to the hardware depth buffer. You can do it in OpenGL, but it's a little weird. In DirectX, you can't do it at all, and you have to do this yourself. Again, your engine may do this for you, Unity does, by rendering with a special shader to get this output texture. The advantage of the OpenGL approach is that it is free. It's there already anyway. You don't need to run another render paths of all the objects in your scene in order to get it.
Excuse me, just a quick question. I'm still very new to Unity. Does it provide support to allow you to use OpenGL or DirectX?
Unity provides both by default. I'll get into this a little more later. Once you're down in shaderland, you can stay in happy surface shaders, and you're mostly protected from platform differences. If you go any deeper, you're going to run into trouble with this. And you're going to have to start caring about which platform the shader is running on and conditional compiling or switching on the platform in order to handle things differently. Because unfortunately, while they are similar, the two APIs aren't really identical in any useful way. DirectX, half-pixel offset, if you know what I'm talking about, shake your fist in anger. All right. So the limits of shaders. One of them is scope. The vertex shader runs for the vertex, has access to no data besides what's on the vertex. This means that you can't, for example, have a vertex shader that does something based on all its neighboring vertices. You just don't have access to that information. Likewise, the pixel shader only knows about the pixel it's running on. Doesn't really have access to data in other pixels. You can get around this with the post-process effects trick of rendering everything to an image first and then looking up into that. But that is now another rendering step. You can't do this all in one single shader. Hardware instruction limits. This is determined entirely by the underlying hardware. I'm going to talk mostly in terms of shader model, which is actually a DirectX term for the different versions of their shader API. OpenGL is fuzzier. It's just simply not as cleanly divided, although the same restrictions apply to what card you're working with. In shader model 2, which is sort of the default that Unity works with, you can have 256 instructions in your vertex shader. It's a good number. You can do a lot with 256 arithmetic instructions. In your pixel shader, you can have 32 texture lookups and only 64 arithmetic instructions. This is an awkwardly tight budget to do anything fancy with. You also have a limit of 4 texture indirections. Texture indirection is when you use the output of a texture lookup to look up into another texture. So for example, I'm doing a depth of field effect. I want to blur things, but only things that are far away. So I look up into the depth texture, and I get a depth value, and then I look up into the image of my scene, but at a distance that is determined by that depth value. This is now a texture indirection, and I can only go 4 steps deep in this before the shader compiler will simply give up and say, no, you can't do that anymore. Also on some hardware, specifically iOS, and their tile-based deferred rendering is called, it's cool. Texture indirections are terrible. As soon as you do any of them, it basically breaks the rendering pipeline. It has to restart a bunch of stuff, and your frame rate drops off a cliff. Shader Model 3, pretty much every reasonable card at this point supports it and is much looser, limited on 512 instructions. That is the minimum for a Shader Model 3 card. Some Shader Model 3 cards support more, but that is entirely graphics card dependent now. If you're at the bleeding cutting edge, you're now up to Shader Model 4 and 5, which roughly corresponds to DirectX 10 and 11. OpenGL has equivalent support. Apple's drivers do not, sadly. Shader Model 1, by the way, was hardware transforming lighting before we really had programmable shaders. So, the big lesson from this is you have to know the hardware you're running on once you're in shader territory. It is unfortunate because graphics hardware is wild and varied and everyone has a slightly different piece of it. And also unfortunate because most modern engines and really most modern software development practices focus on getting away from the hardware as much as possible. And 99% of the time this is a good thing, except when you're trying to get bleeding edge performance out of specialized hardware, in which case you're stuck with it. The last limitation I want to talk about is depth and depth testing. This is a limitation of 3D hardware in general. I emphasize it here because I've frequently seen people say, hey, how can I make a shader that does X, Y, Z, renders my transparent thing on top of another transparent thing? And the unfortunate answer is you can't. Depth buffers track 1 depth value per pixel. You can, depending on the rendering order, overwrite that depth value if you're drawing something closer. But that's it. You can't have multiple depth values per pixel, which is what you need if you wanted to, say, layer a bunch of transparent things nicely. This means that most engines, Unity included, end up sorting their transparent objects. They can't write to the depth buffer, but they need to look up into it. So they sort them roughly by closest to the camera, so they end up rendering in roughly the right order. A side effect of this is you can't really apply a transparent shader to an arbitrary mesh, because if you do, weird stuff happens. Like that. Compare that to that guy. That's what it should look like. It just doesn't know what order to draw most of those triangles in, and it can't because this is all centered around one position. It can't sort anything useful. So those are hard limits. Those are things you just can't do. These are things you have to be careful about in order to get reasonable frame rate. You have sort of 3 buckets of performance with graphics techniques. Your CPU is going to do some stuff. You're going to do some stuff in your Vertex shader, and you're going to do some stuff in your pixel shader, which equates basically to pixel fill rate. Fill rate, basically everything I've worked on is always the limiting factor. Push as much stuff out of pixel shader as possible. Typically, you want to push stuff as far up this pipe as possible, because the farther up this pipe it goes, the less often it executes. Stuff done on the CPU, you're executing it maybe once per model. Stuff done in the Vertex, you're executing once per Vertex. Stuff done in the fragment shader, you're executing once per pixel. There are cases where it's actually cheaper to move things from the CPU to the Vertex shader This is because the Vertex shader typically doesn't have much to do, and most graphics cards have a big dedicated Vertex unit that is sitting idle most of the time, unless you have a very complicated scene. Those three things combined with your scene complexity in terms of the resolution you're rendering at or the number of vertices will determine your frame rate. So again, you have to know your hardware. Sometimes you have to know your hardware in weird, non-intuitive ways. Depending on, for a modern graphics card, and this has been true for 5 to 10 years as far as I can tell, depending on the model you buy, you have a different number of hardware texture samplers enabled. Low-end consumer card typically has 8. Very high-end ones these days have 64 or more. This is the number of textures that your pixel shader can look up simultaneously. That 8 is kind of a pain, because that means that if you ever look up more than 8 textures in a single pixel shader, it does the 8 of them it can, and then has to restart. And suddenly your pixel shader takes twice as long to run for no apparent reason. And again, this is completely hardware dependent. And unfortunately, the number of texture samplers in the low-end card really hasn't changed for many years, because NVIDIA likes to sell people their high-end cards, I guess. So,
sorry, when you have like a low number of textures, I mean, is there any risk of data loss involved, or?
You can, because of floating point precision, depending basically on the operations in your shader, and depending on the floating point precision you use, both in the textures themselves, especially if you're doing a post-process effect, like writing everything out to another texture and looking it up again, you can sometimes lose data as you combine all this stuff. So an RGB texture can hold 8 bits of data per channel. A floating point type in a shader or in CPU land is 32 bits of data per channel. So you have a lot of precision to work with, and typically more than you need for doing simple operations in the shader, but it is possible to start getting strange color compression artifacts if you do a whole bunch of them. Is that what you're asking about, basically?
Yeah.
All right, so in medium to large projects, like Guns of Icarus Online, we have 20 or more shaders with various combinations of feature. Well, I want the alpha one, and I want the specular one, and then I want the alpha specular one. And then, ooh, I got this tiling multi-texture feature, now I want that in alpha and specular and bump mapped versions. And for all of these, we want to support a wide range of hardware, which means having slightly different versions of the shader for all that hardware. And we want to keep all the visual results consistent. And because if you're like me, you're a part-time graphics programmer who has a million other things to do, you want to minimize code duplication so you can maintain this stuff. So this is again somewhat Unity specific, but here's the process I've sort of settled on. All of the actual hard work functions go off in another file that then gets included in the individual shaders. This is terrible procedural C land. You don't actually have objects or modules in any meaningful sense. You just have include files. But you can do stuff with that. In the particular example here of Guns of Icarus, I have one for a bunch of cube map lighting functions and one other include file for some fancy gradient effects. Unity's dependency handling with these is a little flaky. Sometimes you change the CG file and it doesn't recompile the shaders that depend on it. You just have to manually do it then. I don't understand why, it's weird. Every shader then defines a fallback. This is a Unity specific feature, but if you have anything else, anything like this in any other engine you use, I would highly recommend it. And if you are in the position of writing it yourself, I would highly recommend writing a feature like this. The whole point of the fallback is that it determines if the current shader can run on the current hardware. If it can't, it goes to the next one in the chain. If that one can't run, it goes to the next one in the chain. And you can now chain all your shaders together in this big fancy tree, so that no matter where you start in the tree, you can almost start stripping features down and eventually find one that works. So for example, I have a bump map specular shader. Well, if I'm on a really crappy card that can't do bump maps, maybe I can just do specular. Okay, it's a really crappy card. Specular takes up too much frame time, just diffuse. You can't even do pixel lights, have vertex lit. Also, Unity does a handy thing where if you fall back to vertex lit, that's where all its shadow casting passes are defined. So any shader that eventually falls back to vertex lit just gets real-time shadows. Similarly, in one shader in Unity, you can find this sub-shader structure that does that same fallback sequence. So you can now pick alternate implementations, you can control with a level of detail parameter which implementation you use based on user settings, etc. So in this example here, I have all the actual shader work. This is a surface shader that does this just ambient cube map lookup. Up in this one block that gets included by each of the three sub-shaders, each of which manipulates some surface shader parameters. This one turns on a whole bunch of shadows and does a fancy lighting equation. Still fancy lighting equation, but no shadows. Well, not even a fancy lighting equation. So doing this, you still are going to have a whole lot of shader code. It's sort of, it's doomed to be messy by the nature of the beast, but you can try to minimize that at least. Finally, you can write all these shaders. Why would you want to? So the player's perception of your game is going to come from a combination of your rendering method and the assets your artists produce. Or turn that around for a minute, the assets you produce and the rendering method your graphics programmer gives you. This means your graphics programmer and your artist better be on the same page about what you're trying to do. Better be working to the same concept art, get everyone agreed, yes, we can do this, and this looks good, we all like this. Especially in a small team where you don't have the ability to have a huge graphics programming department, a huge art department. Getting these things locked down early and getting agreement from everyone is very important. The grand cycle of life. Someone requests a graphics feature. A graphics programmer goes and implements it and brings it in like a shiny new toy. Artists then take the shiny new toy and go to the sandbox and shovel crap all over it and toss it in the mud. And basically use it in a whole bunch of unexpected ways. And then the graphics programmer goes back and says, oh, what did you do? I better make this better. And it's like, well, repeats. I don't mean to sound angry about this. This is actually great. Seriously. You probably have concept art. Make sure your graphics programmers and your artists both look at it and are both working towards that. This is concept art from Guns of Icarus. What did this tell us? We want some really cool sunsets. We want the clouds to take lighting. We want these various highlights. We want some nice detailed stuff on the Zeppelin. We want cloth and metal and that kind of thing. All of which then informs the shaders that I write and the textures that the artists generate. Focus on what's stylistically important to your game. You don't need to be realistic. Frequently, if you're doing a small project, it's easier if you don't. Do nice tune shading, make it look cool. Or do something completely ridiculous, make it painterly, and it'll stand out. If you're a graphics programmer, you should go learn about painting and photography and filmmaking. Artists for centuries have had all sorts of crazy tricks up their sleeves to trick you into thinking that a 2D image looks 3D, and you can steal a lot of these tricks. If you're an artist, particularly if you're a tech artist, but really if you're a 3D artist at all, learn about how 3D algorithms and hardware work, at least a little bit, so you know the limits that you have to work with, the things you can do easily versus the things that are really hard to do, so that you can make assets that are the most effective possible. Finally, some references, and then I'll shut up and take questions. Shader Lab documentation for Unity. NVIDIA's website has a very nice book about CG and sort of the rendering pipeline in general, which is linked there. It also has all the documentation about the CG language and a bunch of GPU gens books, which have very crazy specific techniques, all available for free on the website. If you're using Unity, there's a little file, unitycg.cginc. This defines most of their built-in shader code, and it's just there in your install. You can go find it and look at it, and it will teach you many interesting things. Another series of good shader books, the ShaderX series. There are 7 or 8 of these now or something. The first few are available for free on the web, put up there by the publisher. And especially if you're learning or if you're working on small projects, the early books in these series are all you need, because the newer ones depend on high-level fancy graphics features that are uncommon or console-specific or simply are more complicated. Finally, that Photoshop blending functions, I cannot emphasize how useful that is. As I said earlier, you may have difficulty finding examples in CG, but there are plenty of HLSL, the DirectX shading language tutorials out there, and they translate very easily into CG.